Hi, this is Bill Foote, and uh, we're taking a Bayesian interlude. Interlude is an interesting word. It's in between the plays. But actually, this is more like play because it's simple, uh, very illustrative, and we might get some insights out of this. I'm going to build the basics of how we do inference, and guess what? It's a 2 by 2 table. Now, in most basic statistics courses, a contingency table might be offered as a model. And here we're going to use it as a framework, a form, a design principle for mashing together data. And data here will be D1 and D2. The actual data that we would populate this would be a 0 or a 1. And hypotheses, two hypotheses. Very simple. Yes and no. True or false. True, yes. No, false. And the ways in which these two notional pieces, our wonderful ideas and our observations from sensory experience, can collide. 5 ways here, 3 ways here, 2 ways here, 7 ways here. So what is this? Suppose we had a situation where we're looking at predation. Predation comes in all sorts of forms. It's interpersonal relationships, it's relationships between markets, between uh, two organizations competing for the same hold on a population of customers, whatever the situation is. And one is attempting to take from the other. Even a joint venture can be conceived this way. And if we understand competition, then we can also understand where collaboration comes in, which is, I guess, the wisdom piece of this sort of work. But here we're simply going through the methodological, really epistemological way of mashing together data and hypotheses. So we build a table, make a little wireframe, a little dashes, they're small but indicative, help us visualize that there is a relationship between H and D, H and D. There are 4 different relationships going on here. We'll use a little bit of mathematical sleight of hand to deal with um, a couple of things. One is to the right here, a wedge, meaning and, a both and, multiplication, the multiplication rule. Anything both and is a multiplication. It's both 1/4 of a quart and another eighth of a quart. Okay. You get the idea from just basics like that. Either or is one or the other. Now, 1/4 of an eighth is different than 1/4 plus an eighth. I mean, again, think of quarts of beer or oil or anything, oil, vegetable or what, some other hydrocarbon. So we're going to use that idea here. And we are going to say and ask the question, if a 0 means there's no predation and a 1 is predation, that's what we observe in the data. We can have 2 hypotheses. And we can have many hypotheses about this, but the simple yes and no hypothesis. We might say, for example, that H1 is 25% of the time we see predation. H2 is 75% of the time we see H2 is 75% of the time we see predation or not. Okay, this is another way of doing it. So I've just chosen the simple binary approach, 0, 1, coding it up here. Now the zeros and the 1 don't actually get involved here. They can, but they're not getting involved. They're just our way of coding something. No and yes, false and true. No, predation, yes, predation. And when we mash together D1, 0, and no, that's the wedge there. Or we could do it the other way around. We can go from no and D1. That's called commutativity. It's commutative. We get the joint number of ways in which this might happen. Now, where are these coming from? They're coming from observations. Okay. We see broad-winged raptors in the sky. Okay, fine. Yes, that's a 1. No, that's a 0. The sky is clear. The sky is not clear. 2 different hypotheses end up being categories, and we're mashing them together and saying, well, 5 times we saw the raptors, and it was clear skies. Same idea. 5 times we observe no predation, and our hypothesis is there is no predation. So this is really in the mind here, over here on the left, H1, H2. This is what we in our bodies and our pencils on a clipboard record as data. So you got the whole thing here already. And this is the joint number of ways in which H1 and D1 can occur. And suppose it's 3 if we do see predation, and under our hypothesis of no, this is like maybe cloudy skies here, clear skies, 3 times. Together, this hypothesis together gives us 8 different ways fanning across the 2 pieces of data that we have. Let's go in the other direction. Just look at D1, no predation. Now, D1, 5 times can occur if H1 is true. 2 times we might observe when H2 is not, that's false. H2 is, yes, true. Predation is true. I get mixed up, yes. But the coding will help us figure that out. And that ends up being 7 total ways that D1, no predation, can occur across the 2 hypotheses. So in machine learning, this is called labeling, effectively classification. Classification of species relative to their genera, a classification of whatever, decisions. Now, the question then asks, let's look across the row first, and then we're going to do the column. Question is, what is the joint probability of seeing 5 relative to all of the ways of seeing the way data mashes together with hypotheses? And if you add all of these up, you can see in the margins of the table, it's kind of called marginal event analysis. We have 8 and 9 make 17. 7 and 10 make 17. They had better. There's a kind of conservation of ways. There's only a total number of ways. It's finite. And they must add up by row and by column. And they do so seemingly naturally here. And this becomes a principled way of thinking in general. So it's 5 out of 17. Now you can work that out on your slide rules, what 5/17 is. We're not going to do that. We can get into the decimal numbering system. We're going to keep this integers and ratios of integers called rational numbers. That's all we're going to keep. It's nice and easy to work that out. But we'll call this the joint probability. And you see I have it down here. The probability of H1 and D1 is 5/17. The probability of D1 and H1, just flipping that, columns versus rows, is still 5/17. So you can't get around that. But now we can get a little bit deeper into what these numbers are by row or by column. Now by row, just pretend all of this is grayed out right now. We're just looking at 5 and 3 and 8, which is the row for H1. And we're going to do some conventions here, mathematical conventions. Just it's really notation. It's an expression. It's not mathematical per se in that sense. It's just an expression. We're going to say, shorthand, the probability PR of H1 is 8/17. We will see H1, no predation, 8/17 times. Probability of H2, 9/17 times. Since this is the entire event space, if you will, the entire universe, the entire set of the ways that we are saying it's yes or no, it's exhaustive, mutually exclusive, wonderful. Hypotheses, good formation of hypotheses. 8 and 9 is 17. 17/17 is everything. 1. And we're going to assign to that the notion of certainty. In and of itself, it isn't certainty. The numbers aren't, but when we see those numbers, that's what we're assigning. So we're building a manifold over the numbers. And then the commas, yes. We're going to say D1 occurs given H1, and this is going to be our convention. This is first. The vertical bar, the vinculum, is conditioned on, or might even use, got to be careful of this one, entails. Okay, it's 5/8. Now what is that? 5 out of 8 possible ways in which H1 can occur. We see D1. Probability that we see D1 given H1 is, now that's why we're using this piece right there. Okay. Now, the next row, the probability of seeing D1 is 2 ways out of 9. And we're going to call these conditional probabilities. Seeing data, conditioned on hypotheses. Now, the whole point of inference is flip that around. What is the probability of seeing a hypothesis? We want to know, is our theory true, and can we use it to predict what might happen, either in between the data points or before the data points or after the data points or some other time in the universe, okay? That's where we're going with this. And here we have, it's the same thing, 2 out of 9, 9/17. So these are, again, the probabilities of the hypothesis occurring at all. Each hypothesis occurs across the data. We can parse out what the probability of D1 is given if H2 is true, 2 out of 9. Now, here's the flip. We went row-wise, now we go column-wise. The flip is the probability that we see D1, which is no predation, that's 0, is 7/17 out of all the total ways. And D2 is 10/17 out of all the total ways. Look both of these, either or, that's an either D1 occurs or D2 occurs. you get all of the ways, again, certainty. In our set of operations here, in our area of operation, this is very straightforward. These are the only two hypotheses, yes or no. We're only talking about no and yes for predation, and we're only observing predation. Okay, that's our small world, very small world. Well, we can now calculate the probability of this hypothesis given this piece of data. It works out to being 5/7. Different than the 8/7 up here. Whoops, sorry about that. Different than the 8/7, sorry, the 5/7 up here. And then 3/10 different than the 2/9. So this is flipping it. This is asking the question, what is the probability of hypothesis one, no predation, that's our hypothesis, our conjecture, given that we see predation? No predation, actually. Given that we see no predation, 5/7. What is the probability of this hypothesis if we do see it? 3/10 less. We're going to call this a posterior probability because we're looking at after we mash together, posterior, after we mash together the data that we have with our hypotheses. We're going to call this probability D1 given H1, well, we often call it a likelihood function. Oh, ramble about that. It's happening within. It's the probability of the data given the hypothesis. I mean, we have two in this case. And we're gonna do a little sleight of hand here because if this is typically what we're given, and by the way, this is typically what we're given, it's a likelihood, and we're going to find the maximum likelihood, the most likely data given hypothesis. We're going to condition that further with another both and. How often do we see that hypothesis? So if we were to take 5/8 and 8/17, so 5/8 of the time we see this data with this 5/8 and of 8/17. That's an interesting idea in and of itself, the both and of those two. The both and of, we see this hypothesis, and given this hypothesis, we see this data. So we see this hypothesis operating 9/17 the time. 9/17 of 2/9 gives us an interesting idea. Okay, so let's use that thought down here. And we're going to derive something very famous from 1763. The Reverend Thomas Bayes, B-A-Y-E-S, came up with it, and a good friend of his posthumously, after his death, published this in the 1760s, I think by 1767 or so. It is based on Abraham de Moivre's Doctrine of Chances. So they were all thinking about this. The Enlightenment project was thinking about all of these things. How do we know? How do we know for certain? We know probabilistically. Let's suppose everything looks like a game of chance. And if the universe is run like a game of chance, remember Einstein says God doesn't play dice. Yes. But it looks like that to us mere mortals, which is what their point was. How much more can we see the great glory of God in God's creation? That was what they were trying to get at. But they were also trying to calculate annuity premium for farmers, for insurance, for you name it. Okay. The whole business of insuring a load in a cargo load in a ship, and there's a lot of storms at sea this season. Will it arrive or not? Either it arrives or it doesn't arrive. Payout, no payout. How much should you charge for undertaking that risk? And then that becomes a whole model of business, whole model of management of organizations. And some people have taken it very interestingly as a model of managing the person. I don't think that's the right way to go. I think that's the grand inversion. And it's all going to be inside of this principle, which comes directly out of the math. So if we believe that the joint probability of H1 and D1 is simply 5/17, and it the other way around, D1 and H1, it's just inverting those two, rows versus columns, or is it columns versus rows? Yeah, this is the column version over here. And this is the row version, up here. Each of those rows and 2 and the 7 you can see on the screen. And that's 17. So let's just calculate out what I just said. Take the probability of D1 given H1. So 5/8 of the time we see this, but only that's of 8/17 of the time that hypothesis is even around. One of the other gives you, look at this, 5/8 times 8/17. 8. 8 divided by 8 is 1. Anything times 1 is itself. We get 5/17 back. So we can therefore say that this notation, this expression, the probability of D1 given H1 times the probability of H1 is equivalent to the probability of D1 and, okay, just waiting to see if you remembered, and the joint probability of D1 and H1. Now, this can be generalized. We can take this table and extend it to the right and down for as far as you'd like. And we can put all sorts of integers and numbers in between integers as you like. We can just make them A, B, C, D and prove this as you like using some algebra. We can also use abelian group theory as you like and create maps and point sets and so on. We don't need to do that. If we believe in the magic of integers and rational numbers and the basic arithmetic algebra, and its commutativity is the key. Without this commutativity, this doesn't work. But it works because of the structure of the table. Think about that because it's an assumption of our analysis. Now go in the other direction. Go column-wise, down the column. The probability of H1 given D1 we said is 5/7. There we go over here. And the probability that we see D1 at all across the two hypotheses is 7/17. 7 divided by 7 is 1. Anything times 1 is itself, and we get 5/17 back. So this left-hand side, probability of H1 and D1, the joint probability, is equivalent to saying the probability of H1 given D1 in our notation times 5/7 of 7/17 times the probability we see D1, which is no predation in our little sentence world here. And they are equivalent. That means that this equation, two things equal to the same thing are themselves equal. Almost a metaphysical principle. It's the principle of identity, if anything. And there's also kind of like a sufficient reason going on there. Okay? If you don't believe those things are at work, pick up a different discipline. No, all human beings think this way pretty much in one fashion or another. We're just putting some structure to it and some notation and some expression to it and coming up with a little bit of logic. And this is what Edward T. Jaynes, Jaynes, and I cite him all over the place, calls the logic science. Yeah. And here we are. The last thing we'll do is if these things here are together, if the probability of H1 given D1 times the probability of D1 equals, flip side, probability of D1 given H1 times the probability of H1. And we can divide both sides. What was the thing we were asking? The thing that the arrow points to. We were asking, how can we find out, because this is inference, from the data, the formation of hypotheses. We've sampled data, and now we're counting the ways. That's where we're coming from, and that's where we're going. What is the probability, our index for hypothesis? We want to know what hypothesis is true or not. Okay. The hypothesis might be a slope and an intercept. Hypothesis might be a proportion. Hypotheses might be the relationship, the very complex relationship between predator and prey, our various parameters. Those are hypotheses. And then we apply data to that and see, well, does our brilliant model work or does it fall flat? Yeah, we can make it work. Yeah, it does work in certain circumstances, and we will tune that. But if we divide both sides by the probability of seeing data, look, algebra comes to our aid once again. And they said you would never use it again. Probability of D1 divided by the probability of D1 is 1. Anything times 1 is itself. We have what we used to say isolated this. Okay. We've normed out the other term. That's what we've done. But that implies, on the other hand, well, we still have this probability of D1 H1 times the probability of H1, often called the base rate, divided by the probability of D1. We put a star next to it because we have found our rule. This is called Bayes' rule. It also allows us to update this. It's called Bayes' rule. And use this rule and verify that the probability of H2 given D1, or the probability of H1 given D2, or the probability of H2 given D2, these are the only possible combinations in our very small little world here, do work out to these numbers, okay, using Bayes' rule, using the rows to infer the columns to infer the rows. But usually we go from the rows inferring the columns in this particular case. That's how we will work this. And you could also check out a very useful master teacher. We have a bunch of master teachers in this area. Daniela Navarro in LibreText, Libretext. Check her out with regard to these sorts of ways of thinking. Look at that. Check out Richard McElreath, definitely. Buy his book. Everybody should buy his book. The most readable stats book I've ever seen, and I've been just doing this for many years to say. These are the things that will hold it together. Very practical, not zero dumbing down. I mean, we're deep inside of some very interesting mathematics here. Extend that thinking. That thinking is logical thinking. It isn't just symbolic logic, as you can see. We actually breathe some life into what otherwise is pure mathematical exercise. And that's what we do as practitioners. Okay. And then we as practitioners come up with problems, and the mathematicians have to stand back and say, gee, wonder how that works out in an algebra, for example, or a field or a ring or whatever structure they're talking about. And we're breathing life into their next set of insights. And then we use their insights and go back and forth, back and forth, back and forth. And that's how knowledge grows. Knowledge. Very, very practical kind of knowledge. So I'm going to leave you with that. Thank you very much for your very kind attention as we explore some very interesting areas on a single sheet of paper. Just label this whole course. Let's all do it. single sheet of paper. And if you can replicate this across several examples, well, it'll become effortless after a very short time. Worth it. I use pencil because I need something at the end of this pencil called an eraser. There we go. Proper background. An eraser. And you may find the same thing. I'll leave you with that. Remember to encourage each other daily while it is still today. And again, thank you for your time. And this will be on the playlist.